Hey everybody, thanks for checking back in. This is homework 10-4, number 4, and it's part B. And you should have gotten A already. You were supposed to calculate the speed of the putty and block system after collision. What happened here was that we had a blob of putty, something that is sticky, flying towards a block on a spring. Now you didn't need to worry about the spring at first, but the putty flew into the block, stuck to it, and then the block and putty moved together with a velocity that we found to be, let's see, velocity of the block and putty. That was 0.239 meters per second. Okay, you should have found that in part A. Now, part B asks us, what is the change in displacement of the spring? That is, how far does this putty and block system move from its original position and compress the spring before coming to a stop? So if we transfer that over here, the initial velocity of the block and putty is 0.239 meters per second. And once it's all the way compressed as far as it can, the final velocity is going to be 0 meters per second. Okay, so we're solving for this displacement right here. How far will it displace going from 0.239 meters per second to 0? All right, we need to turn this into an energy problem, because if you think about it, as this putty and block system are just starting to move together with this 0.239 meters per second, the question is, what kind of energy does it have? And it has kinetic energy. Kinetic energy right here. Well, what kind of energy does it have over here when the spring is all the way compressed? What kind of spring energy does it have? It has potential energy, and it has potential energy wrapped up in that spring right there. All the kinetic energy is gone. The energy of movement has turned entirely to potential energy in the spring. And if we let this problem go a little further, we could expect the spring to push that block and putty system back, but we're not dealing with that quite just yet. So what we're saying is that this loss of kinetic energy is getting less and less, is going to be equal to a gain in potential energy. And we're assuming that no other energy is lost. So really the kinetic energy that the block and putty system has is going to be turned entirely into potential energy. Well, let's expand these out. Let's find out what we, let's write out what we need to find kinetic energy. You guys probably remember that kinetic energy is 1/2, I should put a negative in front of this, times mass. Well, mass of what? That's the mass of the putty and the block together. Whoops, I already wrote M. P and B together, times the velocity squared. Well, what velocity is that? When it first starts moving, it has a velocity of 0.239 meters per second. Velocity of the putty and block, initial velocity of the putty and block squared. Okay, and we set that equal to the gain of potential energy. And if you recall, the potential energy of a spring, it looks a lot like kinetic energy, but it's 1/2 K, which is a spring constant, that's the stiffness of the spring, times X squared. Right here, that's what we want. We want to find X. So why don't we rearrange this to solve for X and then plug in, and then we have our answer. Well, first of all, we can get rid of these right here, because 1/2 on both sides just cancels right out. And so we should probably divide by K on both sides, and then take the square root of the whole thing to get rid of that square right there. So we should say that X is going to equal to the square root of mass of the putty and block system together, times the velocity, initial velocity of the putty and block system squared, divided by the spring constant K. Okay? So what's the mass of them together? The mass is 0.430 kilograms oops, back up there, plus 0.05 kilograms. That's the mass of them together. Now you could probably just add that in your head, but times their velocity squared. What's their initial velocity? That's this right up here. That's 0.239 meters per second. That quantity squared. Divided by our spring constant K. That's 20 newtons per meter, I believe. Yes, newtons per meter. That gives us X. Take all that, multiply it out, take the square root, and what do you get? Should be 0.037 meters. And that's it. That's our displacement. That's our change in position right there that the spring has undergone. So there you have it. That's 4B. Again, we've taken our knowledge of initial and final momentum and turned it into an energy equation, which is going to be very important, especially in this last part of the chapter. So 4B, there you have it. I'll see you on the next one.